In the previous lecture, we started talking about the idea of pipelining, and we saw that there are three different types of hazards that we need to be concerned about. We have the structural hazard, that is when we need to do something but we do not have the resource for it. We have the data hazard, that is when we need to do a computation, but one of the operands that we need to do the computation has not been computed yet, or is not available where we need it. And there was a third type of hazard, that's control hazard. And in this lecture, we'll discuss the control hazards. And this picture on the slide is just to remind us that the word hazard in computer architecture is used more in the sense of something that could go wrong and prevent the pipelining from operating at full speed. Remember that the pipelining is like an assembly line. And if something goes wrong, this assembly line is not going to be able to operate at full speed. So that's the sense in which the word hazard is used in computer architecture. Control hazards happen because there are some instructions that make decision, and those instructions in an assembly program are the conditional branches. And when I have a conditional branch, the conditional branch determines the flow of control of the program, determines which is the next instruction that the program will execute. Remember that in a pipeline, I would like to be able to start fetching the next instruction while I'm doing the decoding of the previous instruction. And but the problem is that if the instruction that I'm decoding is a branch, this branch may change which is the next instruction that I will execute, and therefore I may not know which instruction, or I will not going to know which instruction to fetch next. So this is what we call a control hazard. Which instruction I'm going to fetch next depends on the outcome of a conditional branch that I'm only going to know after I do the computation for the branch. And in that case, what will going to happen is that the pipeline may not be able to fetch the correct instruction. The branch instruction will still be in the decoding stage. Remember, the decoding stage is accessing the register file to obtain the value of the registers, and is decoding, determining that this is a branch instruction. In a RISC-V pipeline, what happens is that I need to compare the registers and I need to compute the target early in the pipeline if I wanted to reduce the consequence of these control hazards that occur when I have a branch. So one solution to reduce the penalty of a branch is to add additional hardware to the design of the processor in such a way that I can do more at the ID stage instead of waiting until the execution stage to perform the computation for the branch. Another solution is to simply stall on a branch. Stall means that I do nothing for one cycle in my pipeline. We saw that in the data dependence case in the previous lecture. That's the idea of inserting a bubble in the pipeline, where I repeat the fetching of the current instruction. And if I think of my instructions as navigating through the pipeline, the consequence of that is that there will be one stage in this assembly line, that's the pipeline, that will be doing nothing. And when that stage gets to the end, I produce no outcome. So if I wait until the branch outcome is known before I fetch the next instruction, then it's like I am sure to have a penalty, because I'm going to be, for example, fetching that add, and then the next instruction that I fetch is the branch, but I don't know what is the next instruction that I have to fetch. So in the next cycle, I will be doing the decoding for the branch, and I'm going to be doing the execution for the add that came before the branch. And instead of fetching something, I do nothing. And then I wait until the stage where I can know the outcome of the branch to fetch the next instruction. And in this case, it's a very optimistic case where I assumed that I was able to have the decision for the outcome of the branch of the end of the decoding stage of the branch. So that will be with the optimization, where I have added additional hardware to be able to make the branch decision earlier. And in this case, I end up with that bubble in the pipeline. And I would have the bubble of the pipeline for every branch that I execute. To try to improve on this solution, one thing that we can do is to use something that's called branch prediction. Branch prediction consists on trying to guess what the branch is going to do and start fetching instructions as if our guess is correct. So this is what's known as speculative execution. You have heard extensively, probably recently, about speculative execution, because it is the branch prediction, the speculative execution because of branch prediction, that led to the security vulnerabilities that became very well known in the last few years, that are the hardware security vulnerabilities that had to then be corrected. What happens is that the pipelines in real processors are much longer than this conceptual pipeline that we have been discussing in these lectures. We have simplified the idea of the pipeline to have only these 5 stages because it's a didactic mechanism that makes it easier for us to introduce the concept and for you to understand what is a pipeline and how the pipeline works. However, in real processors, the length of the pipelines is much longer. It varies between 14 and 21, 22 stages, depending on the design of the processor. And there is a history, there is an evolution in the length of the pipeline. The pipelines used to be between 12 and 14, then they start growing, and they grew all the way to about 22 cycles. And then people realized that those very long pipelines were actually not leading to an increase in the performance of the processor. Actually, the penalties because of the long pipelines, whenever I had a situation that created a hazard in the execution, were too high. So Intel, for example, we can do a history where they increase the size of the pipeline and then they start decreasing again. And today it's settled around 16 to 18 stages depending on the design. But the bottom line is that in real processors, the pipelines are much longer than the ones that we're discussing in this series of lectures, and therefore the penalty of not being able to fetch the next instruction until the branch outcome is known is much higher. So the benefits of branch prediction are much more salient in such architectures. So the penalty of making a branch misprediction is very high. Therefore, very significant resources and significant research have been dedicated to obtain very good predictions. We're going to start with some simple predictions. So we want to predict the outcome of the branch. And we're going to only have stalls if our prediction is wrong. If our prediction is correct, we're going to be able to fetch instruction at the full speed as if we did not have a branch. So in the RISC-V pipeline, one of the simple solutions is to do what we call a static prediction. A static prediction is a prediction that I do for branches without knowing what's going on during the execution of the program. So the static prediction is the same for all programs and for all branches. And one prediction that I can make is that the branch will not going to be taken. And one of the reasons to choose that prediction is because if the branch is not taken, the next instruction that I'm going to fetch is the instruction that comes immediately after the branch. So this is a very simple solution where I keep fetching instructions as if it was not a branch. And I keep filling the pipeline with those instructions. When I find out that the prediction was incorrect, I'm going to have to convert the instructions that I have already fetched into the pipeline into no-ops. A no-op is a no operation, so it's the execution of an instruction that has no effect on the state of the program. So this will allow me to fetch the instructions after the branch with no delay, but I'm going to have to undo or nullify some of those instructions if my prediction is incorrect when I find that out. So here's an example. I predicted that the branch is not taken. So at the branch stage, I fetch the next instruction after the branch, and if the prediction is correct, I can continue execution. If the prediction is incorrect, when I find out that the prediction is incorrect, that instruction becomes a no-op, so that's the equivalent of a bubble in the pipeline. A bubble in the pipeline is simply an instruction that does nothing. That's all that is. And the way I convert an instruction that I already fetched into an instruction that does nothing, the processor is designed in such a way that, remember that I have all these control lines that go into the data path and activate each one of the muxes and each one of the units that do some operations, such as the memory, the register write, the memory write, etc. So one way that I can convert any instruction into a do not instruction is to simply make all the control lines equal 0. So if I make all lines equal 0, the instruction is going to go through the pipeline, but no register will be written, no memory will going to be written, and the instruction is going to have no effect on the state of the program. So I can convert any instruction into a no-op by simply converting all the control lines to 0. So this is the case with the prediction incorrect. And that's how we call this squashing the instruction. So the instruction, in this case, we would say that the load got squashed in the pipeline because there was no effect on that load. However, that branch prediction, although very simple to implement, will produce many incorrect predictions. So I want more realistic predictions. And again, I will continue with static branch prediction. So I could base my prediction on the typical branch behavior. And here I can use our knowledge of how programs are written to make some guess on the prediction. For example, if I write a loop, the branch at the end of the loop is a branch that will go backwards to an instruction that has already been executed before. So the displacement in that branch will be negative because the target of the branch comes before the branch instructions. So we call that a branch backwards. If the branch, the target of the branch comes after the branch in the order of instructions, that's a branch forward. So if the displacement of the branch is positive, I have a forward branch. If the displacement in the branch or the immediate value in the branch is negative, I have a backward branch. So one way that I can do my prediction is that I can predict that the backward branches are always taken. And the reason to do this prediction is that backward branches appear in the end of a loop. And whenever we have a loop in our code, we tend to execute the loop many times. So there will be many times that that branch will be correct, and only one time when I get out of the loop that my prediction will be incorrect. The other thing that I may want to do, I may want to predict that forward branches are not taken. That prediction is a little bit less obvious, but you have to think about how programmers tend to write code. And the idea in the production of code, when I'm using this kind of prediction, is that programmers have a tendency of first putting as the then part of a conditional the piece of code that's more likely to execute, and put in the else part the piece of code that is less likely to execute. This is very personal and it depends a lot on the programmer, but I could also bias my compiler, because remember, when I convert, for example, a C if then else statement to assembly, I have an option of putting the then or the else block first and flipping the condition in the branch. So I could bias my program to have branches that are usually not taken if they are forward, by simply using that intuition in the code generation in my compiler. But those predictions, those static branch predictions, can still produce quite a bit of wrong predictions, and especially in processors that have longer pipelines, the penalty for a branch misprediction can be quite high. So one thing that I can do is to use dynamic branch prediction. Dynamic branch prediction will take into account the actual branch behavior in the last few times that the branch was executed. And this can be based only on the behavior of the current branch, or it could be based on the history of this branch and other branches nearby. there is very extensive research on dynamic branch prediction, and we cover it extensively in 429. We don't have enough time in 229 to cover everything about dynamic branch prediction. It's a very interesting field of study, but basically what I can tell you is that we have tables of counters that are internal to the processor that are updated every time that a branch is executed with what was the outcome of the branch at that time. And I have these finite state machines that are the prediction states. And I can go from predicted taken to predicted not taken based on the history of the branch, and also based on the history of branches that came immediately before that branch in the execution. And the idea for prediction here is something that we use in other areas of life in general, is that we assume that the near future can be predicted based on the recent past. So the recent past of the program should continue in the near future. So we're only going to be making misprediction when the program changes behavior. When I make a wrong prediction, like before, I have to stall, I have to make the instructions that are the wrong instructions in the pipeline be squashed and become no ops, and I need to update the history, and I need to refetch the instructions that are the correct instructions that I missed fetching. So branch hazards, if the branch outcome were to be determined at the memory stage, then this picture illustrates that I would have 3 instructions that would be incorrect if the branch prediction was wrong, and they would have to be squashed, and the slide indicates that I'm going to be flushing or squashing these instructions by setting all their control lines to 0. For dynamic branch prediction, as I said, the pipelines are much bigger. That's why I say deeper and superscalar pipelines. The branch penalty is much more significant. There will be a branch prediction buffer that's also known as a branch history table that records the history of all the branches that got executed. I will index this table with the address, actually some of the bits of the address of the branch instructions. And I'm going to store the outcome of the branch in those tables, whether the branch was taken or not taken, and I'm going to track this history. When I want to execute a branch, I'm going to take the address of the branch, I'm going to go into that table, and based on the value in that table, I'll be able to predict what is the outcome of the branch next time. And I'm going to start fetching either from the fall through or from the target of the branch. If wrong, I'm going to flush the pipeline and I'm going to flip the prediction. So I'm going to go in my table and say that prediction was wrong. I'm going to make a note of that, and I'm going to fetch the correct instructions. However, if I make a prediction and the prediction is correct, I still need the branch target address, because if I predicted the branch is taken, I need to know where the branch is going. And computing the target address also takes time, because remember, I need to take the immediate value from the branch instruction, and I need to decode it and add to the PC to obtain the target. So at the time that I need to do the prediction, I do not have the target address obtained from the branch instruction. There will be 1 cycle penalty for a taken branch if I do not have another way to find the address. So one idea is to have a small buffer inside of the processor. All processors have that. That is called the branch target buffer. The branch target buffer is like a cache for the target addresses. So whenever I execute a branch, not only I record the outcome of that branch in the branch history table, I also record what was the target of that branch in my branch target buffer. So I will index this branch target buffer by the address of the program counter, actually be some bits of the address of the program counter, and I will go and check this buffer if I make a prediction that the branch is taken. So if I predict that the branch is taken, I get the target address from this buffer, and I fetch instructions from that target address. So of course, a number of things can go wrong. For example, the target address could be incorrect, or I could not have the target address, or I could make the branch prediction could be incorrect. In both cases, I will need to go back and restart from the point where I started doing things wrong. Branch delay slot. There are some architectures, such as the MIPS architecture, where the instruction that appears immediately after a branch is always executed. This is called a single branch delay slot, and the idea here would be that the instruction that appears in the assembly immediately before a branch will immediately after a branch, sorry, is always executed as if the instruction appeared in the instruction in the sequence of instruction before the branch. The idea here is to reduce the branch penalty by having in the order of fetching, the instruction that's fetched immediately after the branch should always be executed. Of course, the branch itself, the branch condition cannot depend on the outcome of that instruction. The RISC architecture does not have any branch delay slots. So when there is a branch delay slot, there are two possibilities. I have an instruction as the compiler or the assembly writer can find an instruction to put in that position, and if you cannot find an instruction to put in that position, you have to put a no-op instruction, in which case is the equivalent of always having one of those bubbles. So the big picture for control hazards is that pipeline is very important in the design of the circuit or the design of a processor, because it increases instruction throughput. Remember, pipeline does not reduce instruction latency. The time to execute a single instruction in the pipeline is the same or even higher than without the pipeline, but I can execute more instructions per unit of time. So it allows me to execute multiple instructions in parallel, which increases the performance of my processor. Does not reduce latency and is subject to hazards. I can have structured data and control hazards when I execute in the pipeline. The instruction set design can affect the complexity of the pipeline implementation, so the instruction set design is very important. So that's what I had for the control hazards lecture.